Do not swear?
Because
Because it ran out of time in the third hour.
What happened last time?
they ran out of time.
No, I mean last time we recorded, I remember something that happened.
Banana peppers.
How do you define bad?
Our class.
You're just saying art clip. Okay, inscribed angle. We try something funky today. We take that vertex. So for instance, when we had a central angle, we had a vertex at the center of the circle. For an inscribed angle, we're going to move that vertex someplace else. And that's pretty much what we're going to do for the rest of the chapter, just move that vertex all over the place. So that's an inscribed angle. Angle DOG is an inscribed angle. The question for you, hey, did you get new shoes? Oh, those look brand new. Where? Shut up, how do you keep them so clean? I had mine for like 3 days, they look like I was running through mud.
You can clean it with toothpaste.
Yeah, my mom does that.
Or you just
I just put mine in the wash.
She soaks them in OxyClean and then she takes toothpaste. They do? Really?
I put mine in the wash by
I've literally
myself.
ran in the mud and then
Anyway, sorry, what's an inscribed angle? Right.
An angle inside the circle that is not made in the sun.
Okay. So let me draw some pictures and see if,
That
I'm gonna
touches
I'm going to draw some pictures that satisfy your definition and see if you think they are also an inscribed angle.
Alright.
Okay? Can you say your definition again?
Um,
An angle inside the circle that's not at the center.
yeah.
Is that an inscribed angle?
No.
It's not. Okay? You want to change your definition?
Yeah.
Go.
That touches the outside. Or that is made.
That touches the outside. Round the outside.
vertex-
Round the outside. I'm sorry, what?
The vertex has to touch the outside.
The outside of what?
The circle.
Well, there is no outside of a circle. A circle is a circle. Okay?
The edge.
There is no edge. Okay, remember, is this light green part of the circle?
No.
No, I just color it in so we get all fancies in my pansies. The circle is actually the dark green. So I understand what you're saying. I'm just being a jerk about your vocabulary. So where do you want that vertex to go?
To touch the circumference.
How about just the circle?
Yeah, the circle.
And can we put it on the circle?
Yeah.
Okay. So you want an angle whose vertex is on the circle. That's it. That's your definition.
Yeah.
How's that sound?
Sure.
Sounds great, right?
No. Yeah. Inside.
We're getting warmer. Inside the circle? What's inside the circle? Because I can't put the vertex inside the circle, it's also on the circle. Okay.
An angle on the circle that has to extend on the inside of the circle.
Has to extend on the inside of this. Okay. Something like this.
Well,
Right. I'm not done yet, but.
yeah.
Oh, that's what you mean by extend. Okay. What about
Yeah,
that?
yeah. Both sides have to extend the angle.
Both sides of the angle
They have to like.
have to like.
Oh, I can't explain it.
Mark?
An angle that has the vertex on the circle.
Okay, stop. Do we all agree on that part?
Yeah.
Okay, good. So we don't have to argue about that anymore. The vertex is on the circle. Good.
And that points inside the circle.
And points. How do what? What do you
Like-
mean? What points?
Like.
Oh, do you mean like this points or
Yeah, I mean
like dot points?
I mean like this points. Those are.
This will work
inside
well
the
on the
circle.
video.
Yes.
Okay.
Yes, like this.
So this inside the circle.
This inside the circle.
Okay, so this inside the circle. So if I line that. All right. Wait. Say it once more. Let's see if I can find a counterexample. An angle whose vertex is on the circle and
And has its lines going inside the circle.
lines,
Or
Rays.
rays, are inside the circle.
Yeah.
The whole ray is inside the circle.
Well, part of it because a ray goes on forever.
Part of the ray is inside the circle.
Yeah, I mean like in DOG the rays aren't fully inside the circle, but they are mostly inside.
All right, give me a second. Let me think about this. I don't know. if I have a counterexample. That might work. Part of the rays are in the circle. Yeah, I don't think I got a way around it. I think you nailed it. Okay. Vertex is on the circle. Sides of the angles. Part of the sides of the angles are in the circle.
Yes, or just sides of the angles.
Sides of the angles
If you
are.
want to be simpler.
Wait, so what is the relationship?
You don't like his definition? You want to use mine instead?
Sure.
Mine's pretty much the same thing. I just got chords involved. If my clicker would work. Nope, wrong stop. Hold on. Okay. Sides contain chords. Okay. Same thing. The picture on the left is what we're looking for there. I just didn't extend the sides into rays. I just stopped with the chords. The one in the middle doesn't work. We're never going to talk about that, those rabbit ear looking things in the middle. We will, however, look at the right example where one of the sides of the angle is a chord and the other one goes flying off into nowhere. We deal with that later. And these are called inscribed circles because they're inscribed in a circle. Bye.
Bye.
Miss you.
Uh,
See you tomorrow. Okay, good. Tomorrow's Friday. You bringing treats for everybody?
No, Mary's in a regular.
Oh, that hurt.
Why would she be?
What's that?
Why would she be drinking?
Why wouldn't she? It's Friday.
it's Friday?
Tomorrow.
Oh, dang, you scared me.
No, today's not Friday.
Maybe it's, yeah, we can mess with this.
Oh, come on. What are we doing here? Okay, so now we know what an inscribed angle is. Now we need to talk about the relationship. Whoa, itchy trigger finger there. Between the angle and the arc. So first of all, here's some new terminology. When I have this angle, and I probably should have talked about this in one of the earlier sections, but when I have that angle, which happens to be an inscribed angle, it's going to hit the circle and intersect an arc. That arc is called the intercepted arc. It's the arc inside the angle. This has nothing to do with this illustration, but what is the relationship between arc AEC and arc AC? Mike.
One is major, one's minor.
Okay, what else? What's the relationship between the two? How do the two relate to each other? No, Ryan?
Add up to 360.
Beautiful, they add up to 360. Remember, all the arcs in a circle have to add up to 360. Okay, so we got an intercepted arc, right? Oh, I just told you the answer. I was going to ask you this question. There's the relationship. The intercepted arc is half the, the inscribed angle is half the measure of the intercepted arc. Or the intercepted arc is twice as big as the angle. Okay, so if angle ABC is 105 degrees, then arc AEC would be 210. And I've got a cool little demonstration of that. Okay, so I got a circle there. And I drew an inscribed angle inside that circle, and it intercepts an arc AC. So then I measured those two things. Angle B is 21.57. Arc CA is 43.15. And then just to check my math, I divided the two. Now the weird thing about this program is it does the calculations always. So it's sitting there doing calculations over and over again. This illustrates the idea for one particular case, but one particular case isn't going to prove it. Okay, just because something happens once doesn't mean it's going to keep happening over and over again. So we can take this point C and move it. Okay, and you see what happens. The arc measure here, or sorry, the angle measure here changed. The arc measure changed, but they still give us the ratio of 0.5. That 0.5 is hard to see. In fact, it's impossible to see, but it's actually redoing the calculations every time. I didn't just type in 0.5 and say, oh yeah, look, it's a half. So it's giving you that relationship between the angle and the arc. Any problems there? All right, let's put this over here. Now here's the weird thing. What just happened? All right.
Move the vertex.
Yeah, what else?
Nothing else really changed.
There you go. Why? If I take B and move it over here, why didn't any of those measures change? Go.
Because A and C didn't move and those mark the length of the arc,
Mm-hmm. Keep going.
meaning that, well, an arc is, like, an arc corresponds, an arc length corresponds to an angle measure, which means if the arc didn't
Arc
change.
measure corresponds to an angle measure.
Yeah.
Okay.
Which means if the arc measure didn't change, the angle measure didn't change.
Good. No matter where I move B in this scenario, it's going to stay the same measurement. Okay, is everybody good on that? All right, now, what just happened?
Change, right?
Yeah. What changed?
Can you do it again?
Yeah.
Blah.
Okay, we're good to go, we're good to go, we're good to go, everything's fine, and then blammo. What just happened?
It's the opposite.
Be more specific, Tom.
Well, can you go back again?
Also your virus definitions.
Yeah, I'm
If
good to
you
go with the
add
virus.
64.89, then can you go over again? To 115.11, it's 180 degrees.
Why?
Because the angle is like inverted now.
What do you mean by inverted?
It's inverted.
Let's go back over here. Okay, let's not. Let's go back over here. Where's the intercepted arc?
There.
Technically, that is a true statement. Which one is the intercepted arc here? AC, good. And then angle B is half of AC. Now I move this over here. Now what's the intercepted arc? Give me colors.
Green.
The green one, right. So that 1/2 relationship no longer exists. This is still measuring angle B, but it's measuring angle or arc AC. We don't want arc AC there. We want the big green arc.
The ratio changed.
Correct, and that's why that ratio changed, because I'm not comparing an inscribed angle to its intercepted arc. I'm measuring or comparing an inscribed angle to some other bizarre arc which has nothing to do with it. This is the one that's going to work. Or just drag it over there. What the heck? There we go. That's what we're concerned about. Vertex is on the circle. The intercepted arc is twice as big. Vertex is on the circle. The arc or the angle is half of the arc. Either one, it works the same way. They're just an inverse relationship. So answer those two questions. Be bashful about busting out that calculator if you need it. You shouldn't, but if you do. Paige, how big is our angle MPQ? This one.
Oh wait, sorry, 70 degrees.
Nope. It seems silly early in the game to start asking this question, but I'll get you indoctrinated into it anyways. The first question you want to ask yourself when you're dealing with angles and circles is, where's the vertex? Because right now we only have two scenarios. The vertex is either at the center of the circle or it's on the circle. So if it's the center of the circle, what do we know about the angle?
Same as the arc.
Same as the arc length, correct. Second scenario, it's on the circle. What's the relationship between the arc and the angle on the circle?
Double.
Right, the arc is double the angle, or the angle is half the arc. So, how big is MPQ? Good. Angle is always smaller than the arc. Staying with that idea page, how big is arc? Puma Narwhal. Your geometry's right, your math is bad.
Yeah.
What's 56 times 2? Good. Again, arc is bigger than the angle measure. Let's see, what if I did this? Call that to x. How big is angle PXN? Pass it. Good, 112. Because again, where's the vertex? At the center of the circle, so therefore the angle is equal to the arc. Find the measure of angles 1 and 2. I'll give you a hint. If you can get one of them, the other one is easy, based on that sketchpad demo we just looked at. Marion, how big's angle 1? Go ahead, I can wait. I'm not going anywhere. Where's the vertex? Okay, what's the relationship if it's on? How big's the angle 1? Beautiful. Oh, Marion, how big's angle 2? Why? I didn't hear you, I'm sorry.
They both have the same ST as like the
Yeah, not chord.
arc.
Arc, good. Oh, Marion, how big is angle 3? Okay. Marion, how big is angle 4?
34.
Uh-huh. You get the idea?
Yes.
Yeah, and that's the same thing as when I dragged B all around the outside of that circle, it would stay the same. Okay so far?
Yeah,
Yeah. Well, okay, did you read that?
Yeah.
Yeah. You got, doesn't matter where I put that angle, if it hits the same arc, they're going to be equal because they're always a half. A half of the same thing is still a half. And we're going to skip this because all that does is illustrate. It just did what Marion did, but now we throw in some algebra. That angle is equal to that angle because they both intercept the arc FG. So you would set those two equals, solve for x, plug it back in. Life is good. Okay, great. Let's move on to something more interesting. This is huge. That angle, B, is inscribed in a semicircle. How big is angle B? That's it.
90,
Why? Or why not?
because AC is 180.
Beautiful. Angle B must be 90 degrees. Anytime you have an arc inscribed in a semicircle, it's going to be 90 degrees for the exact reason she just explained. Okay. This is a diameter because it passes through the center of the circle. That makes that arc a $180. That vertex is on the circle, so it's half of the arc measure. Whoops. Did you get that? We're good?
Wait, what? You say that again.
AC is a diameter. That makes this arc AC a semicircle. Measure of a semicircle is 180. The vertex here is on the circle. It intercepts that semicircle. So it's going to be half of the semicircle measurement, half of 180, 90. So angle B is 90. And no matter where I drag B over on this half of the picture, it's going to stay 90. If I drag it to the other side of the picture, what's it going to become?
90.
90. Because the other side's still a semicircle. We're running out of time here. We're going to skip this example also. If you want to work through it for some strange reason, you can take a look at the slideshow or watch the video. But notice that angle 3 and angle 4 intercept equal arcs because it tells you the arcs are equal. What can you tell me? What's the relationship between angles 1 and 2? Katie, what's the relationship between angles 1 and 2? Nope. Is that a new shirt? That's really nice. They're complementary, very good. Yeah. Meaning what? They equal 90. Why? Right. Why? Ryan.
Because you know angle T is 90 because PS is a semicircle, or it's a diameter that creates.
Which makes PTS a semicircle. Okay, good. This is what's called a cyclic quadrilateral. It's a quadrilateral that's inscribed in a circle, meaning all 4 of the vertices are on the circle. Has to have all four vertices on the circle, or it's not a cyclic quadrilateral. It's something different, and this theorem won't apply. But the theorem says if all 4 vertices are on the circle, then the opposite sides are supplementary. Tom kind of recognized this in the Sketchpad demo. So for instance, how does this arc compare to angle B? What's the relationship between arc ADC and angle B? Tessa.
It's still.
Correct. And then if we change colors here, what's the relationship between angle D and that arc ABC? Right?
Angle D is half.
Good. What's the relationship between the blue arc and the red arc?
They equal 360.
They equal 360. So if B is half of the blue and D is half of the red, and the blue and the red add up together to give you 360, then D and B together have to be equal to 180. It doesn't tell you anything about individual angle measures, just the sum of the 2 angles. They're supplementary. Okay. Same is true with A and C. We could draw different arcs there going from D to B and from, or DCB and DAB, and you see the same relationship.